So this is my first video of like placement day preparation one. Basically, this uh, currently I'm studying like sequential um, logic design and with some part of STA. Like most of the part I will discuss STA, static time analysis. So basically, this is a bistable circuit, fundamental building block of the other state element. So here are some kind of bistable circuit. There are two outputs, like here is q and here is q bar, and this is like I1 and I2. So just like not gate, and no inputs, there are no inputs, so basically whatever the output, that input of the next gate. So this is like bistable circuit. So analyze this circuit. So if suppose my q is 0, then this 0 goes to here, and this 0 here 0 convert to 1, and this 1 convert to again 0. So it is always in a like stable position, you can say bistable. Here 1, here 0, again 0, again 1. And if I analyze this circuit, then I think realize the same thing again. So if suppose here 0, 0 to here, here 0, 0 goes to here 1. So if 0, if q equal to 0, then q are equal to 1, and this one goes to here, and this one goes to again 0. And bistable circuit analysis. So previously I already analyzed the circuit. Now you can see here, like if here is 1, here is 1, so here to here 1 to 0, because it's a inverter, right? So that's why 1 goes to 0, and this 0 comes to here, and this 0 goes to 1 again. So this is the analysis of previous circuit. So bistable circuits store one bit one bit of the states in the state variable q or q, something like that, q bar. Here's the bar, but there are no inputs to control the state. Basically, there are no input was there, so control states will be not present. This is the output of q, but this output is the input of this I2 inverter, and here q bar is the input of this inverter I1. So now jump to SR latch. Basically, SR latch is nothing but there are two input, one is S and another is R. So S means set and R means reset. So uh, if we put into, here is OR gate. So basically, first we, like suppose in a NOR gate, it's a NOR gate, sorry, not OR gate. So if suppose my NOR gate input is A, B and output is Y. So if the 0 0, the four condition will be possible: 0 1, 1 0 and 1 1. So if we need output Y, so then 0 0, then what is my output? 0 0 or is 0, so nor is 1 0 1. So output my 1 1 plus 0 or 1, and nor 0 again 0 again 0. So we realize that if my one input of NOR gate is 1, then my output is 0. So here we check, if my, suppose this condition, my S is 1 and R is 0, then this is 1 and this is 0. This is my 1 and this is 0. So if this is 1, then we know if one of my input is 1, then my output is 0. Here 0. And this 0 goes to here. This 0 if goes to here, so R is my 0, R also my 0. So 0 0, you go to the truth table and see that is 1. So if my AS is 1 and R is 0, so always it gives 1 0. Q is my 1 and Q bar equal to 0. In suppose my previous state is like something 0, so it not depends on the previous state. Whatever the uh, whatever the states, that does not matter. So if we give A is equal to 1 and R equal to 0, my output is like next state is Q. Q is 1 and Q bar obviously 0. So now I analyze the this part. So basically A is equal to 0. So here is 0 and here is 1. So now see, if my one input is 1, then what is my output? If my one input is 1, then my output is 0. Okay. So if it is 0, then these goes to here. Like N2 NOR gate input is 0 and 0. So whatever the what is the output? So 0 0 again 1. So we see that if my input is S equal to 0 and R equal to 1, that time Q equal to 0 and my Q bar equal to 1. So basically it's a reset. If we see that Q equal to 0, so this is called reset. So basically this is the next output, Q plus or Q bar plus. So this is the next output. So my previous output was maybe something 0 or 1 or 1 on 0, whatever. So that does not depend. So my next state does not depend on this previous state. So whatever the input, like 0, if we give 0 and 1 in S and R, so my output is always like next state is always Q. In Q equal to next state equal to 0 and Q bar is 1. So this is the condition of reset. So now if I give 0 0, both are 0 0. So what happened? If I gave both 0 0, here 0, here 0. So if suppose my Q, Q equal to, I assume that here is 0. Because if 0 0, if NOR gate both are one input is 0, so I can't comment that my output is Y, my output Y is 1 or 0, because just assume here A is 0 and A is here also 0, but it depends on the B we don't know. Like here is A and here is B, two input. So I can't comment that my output is something like 1 or 0. So I assume that my output is here 0, that Q is initially 0, so previous state is 0. So if my 0 goes to here and also here is 0, so 0 0, my output is 1, and this one goes to here. So if my this goes to 1, then 0 1, my output is 0. This is the condition, of holding condition. So whatever your previous state output, that holds in next state also. If suppose my if suppose my output is here 1 and here is 0, so what happened? If here is 1 and here is 0, so and my S and R both are 0. Okay, so I assume that Q is 1, so this Q goes to here, means here is 1, and this 0 and this 1 gives me the output. So basically 0 and 1 gives me the output of 0. You can see this is 0 and this 0 goes to here, and this 0 and this 0, what gives me the output? That is 1. Again, it's a holding position. So S and R is a hold condition. whatever the my previous output that holds in the next output, next state. Now analyze S and R both are 1. Let's assume if my S and R both 1 are like 1, then so no matter what, if my NOR get 1 input is 1, then my output is always 0. No matter what, other we don't see even the B input. So if there are any input is 1, then my output is always 0. So here is 0 and here is 0. So this condition is violating each other. Basically, if my q is 0, then q must be 1. But here q is also 0. So or vice versa. So this condition is not possible. So S and what R is not possible. So this the condition in SRLH not possible. Okay. So this is the analysis of SRLH, whatever like S and 0 or something like that. So initially is 1 or 0, then Q1, Q was 0, is 0 R1, so Q1 is 0 R0, so my previous state Q preview like that is 0 and R0, then you can see here the total analysis I told already. So now SRLH symbol. So SRLH is symbol is here. So you just need draw a box. Here R, here S, here Q, here Q bar. So you can also change like something like that. You can also write here S, here R, here Q, and here Q bar. So no, it's not like you can here write here also SRLH symbol and must do something to avoid invalid states when SRLH. So I already told that when is my A's and R both are 1, so it's a invalid state. So must do something to avoid. So there we go for next latch like JK latch we invented, like not we. SRLH stand for set and reset latch. Store one bit of states queue. Control what value is being stored with S R inputs. Set makes the output 1, S equal to 1, R equal to 0, and Q equal to 1. So this is set condition that I already told, and reset condition make the output 0. So my Q should be 0. So that is my reset condition. So for reset condition, S equal to 0 and R equal to 1. So now my D latch internal circuit. So before that, okay, explain D latch internal circuit. So basically, D latch is nothing but whatever the here is D, here is clock. So whatever the input you gives after the just assume whatever the input you gives here, if the clock pulse will apply, suppose clock pulse it's a positive clock, so it's basically latch. So in the in this level, if this circuit will on, so that time whatever the input you gives, that will directly appears in queue. Like your next state will depends on the your D input basically and clock. If clock is your one, then this input goes to the output directly, no matter what. Like your previous key was like something holding something zero value, and now you gives one, then it will change directly, no matter what. And this is the actually basically the SRLH, and this SRLH how to make a D latch circuit by using SRLH. So basically we can make this circuit by like excitation table, basically excitation table and the truth table of the ether. So here I can do something. How it's big. Okay. So how to make SR latch by using SR. Okay. First up we see SR latch, SR Q, and my next state Q plus, and this is also D. Basically this is the D truth table also. So here is my 0 0 0 0 0 1 0 0. Sorry, not 0. Here 0 1 0 0 1 1 1 0 0 1 0 1 1 1 1 1 0 1. Now we see what's my output. So if 0 0 in SRLH we see, if my input is 0 0, then it's hold the value like whatever the in my previous state, that is 0, so it's hold, and my q plus equal to 0 again, and here 1 again. But when it is 0 and 1, so set equal to 0 and r equal to 1, so basically reset is my high, so that my next state equal to 0 both, like no matter what is your previous state here is 1, but it does not depend on previous state. The s is equal to 0 and r equal to 1, so my q plus equal to 0 also. And here again the set condition, so 1 1, and this is the invalid condition. And what is the d? D is my depends on this, so this is my d basically. So 0 1 0 0 1 1, so this is my d. So if I want to make a truth table like d, how to make d? So basically, sorry, so s r, right? So I want to make a d flip flop by using sr latch. So here is my 1. So where is the 1? Like last 4 bit my 1, and if my last 4 bit 1, so I need q plus means d. Sorry, this is not like that. Basically I assume q and q plus. So q goes to 0 to 0, 0 to 1, 1 to 0, and 1 to 1. So what is my s and r? Like this, or this is my d basically. So 0 to 0, what the condition, two condition will be possible. So if when is reset is my high, so that time it is possible, and also when the my holding condition. So for reset, that is s equal to 0 and r equal to 1, and for holding both are 0. So as equal to always 0, but r, that is like 1 and 0, 0 to 1. So two conditions are possible. One is sorry, not two conditions here possible. Here's only I think one condition is possible, that is 0 to 1. So it is set, otherwise it is not possible. I think set means uh, 1 0. Otherwise in JK flip flop it is toggle mode, but here it is not possible. And 1 0 1 0. So if my set is like reset is high, so that time it goes to 0, so 0 1, and 1 1 1 1. How is this, is it possible? So suppose 1 1 means like holding either or either set. So these two conditions are possible. So holding means 0 0 and set means 1 0. So my this bit is changed and this is always I think 0. Huh? If I want to make like what we gives to the input of S, then we just go through this circuit like what the headphone is got. So here is my S, this is S, and this is my Q, and this is my D. Okay, so Q is 0 1. So basically here is 0 and here is 1, here is 0, here is 1. So Q is my 0. So like either this or this. Uh, Q D equal to my 1. So if D equal to 1, then this is 1 and this is cross. So 1 1. So both are 1 means like that this is cross. So this is my is equal to D. So is equal to D. And if we goes if we need R reset, then again truth table, sorry KMF. Here is Q and here is D. So 0 0. Both are 0. So here is cross and this is 0 1. So 0 1 0 1. So this is 1. No, sorry, this is 1 0. I think this is not. This is. So it's D bar. R is equal to D bar. So like its circuit look like this is SR latch, S, and this is R. So just like that. If we give 0, so here 1. If we give 1, here is 0. And this is Q and this is Q1. So this is basically D latch. Let's see. So basically here nothing but one clock is one AND gate is uh, added extra just for clock multiply like when my clock is on in this period here my clock is on that time it gives its s goes to like whatever the d s into d and clock. So that time only clock, if my clock is high, so d is goes to here and d bar goes to here. So that's the only that's for like and get there using latch internal circuit. So here you can see that I already told whatever the like 0 to clock 0 and d nothing but then x bar something like that I already told. Two input clock and d functions, the flip flop samples d on the rising edge of the clock higher. So it's a like flip flop in previously d latch internal circuit. So it is flip flop symbols, d flip flop like this, and the clock signal there was no such as clock in here. Like in here, diet like whenever the your clock is one, that time it goes to like your AND gate will be work. A flip flop is called an edge triggered device because it is active on clock edge. So this is my clock, something like that. So if it is positive edge triggering, so in this period it's work. Like suppose my input is like this. So what do you see that here. Here I get clock. So if I get clock here, okay. If I get clock here, then we see here that my previous output is 1. So what is my output? So here I say it is D. So and what is Q graph look like? So Q is here, here up to here. Here is 0 because there is no clock. This is clock. So no positive edge triggering. So here up to 0. But here it see that my D is 1. So it's hold the value up to when when it's wait for negative clock. So when it comes negative clock, like again the positive edge triggering, that time it's again work. So it see that my previous input is 0, so it goes down and it gives the output like that. Okay. And if we want to know like how positive edge clock is working, so basically the positive edge circuit, here is the positive edge clock. So this is my clock that goes to, like suppose if I make a graph, this is my clock. Here we what we do here like that. So I need a positive edge clock. So in here, in a short period of duration, I just uh, trigger the circuit so such that my circuit is on small period of time, and if my circuit is on, so that time what's the value and D, like 0 or something 1, so that will goes to directly Q. So if my circuit is on for small period of time, so that time whatever the value in Q, so if it is on, so then it changes, and after that it holds the value. So just like that. So in here small period of time its circuit should be on. So this is my positive edge triggering and how circuit look like. So if both are 1, so that time only it will be 1, or otherwise your circuit will be 0. So 1 0 0 0 1, 0, both 0, then 0. Sorry, 0 1 0, and here is both 0. Okay. So circuit is nothing but you take and gate. Here is clock, and your something delay, that is not get, and this is something delay. I assume there's a T, and this delay. So if here is 0, so after some delay it will be 1, and like that. If my 0 is previously so long time, this is 1 long time, but somehow suddenly we change the 1, so after t second it goes to 0. That's the thing we happen. After t second it goes to 0, and it's also goes for a long time, and my suddenly input is like this is the clock actual, so my input is 0 again. So after t second it goes to 1 again. So this is my 1 to 0, it's jump to 1 to 0, but my this circuit, this clock will not goes to immediately 1. So after t second delay it goes to 1. So this is the positive edge clock triggering circuit. And also negative edge, what we do in negative edge, like we had 0 0, right? So in 0 0, in which condition it will gives me the output. So if it is 0 0, so here I want to operate the clock. for negative edge triggering. For negative edge triggering, if we want to operate the circuit in here, so my output, sorry, circuit look like both are 0, both 0 equal to 1. So in which condition gives me the both 0 equal to 1? So if I take NOR gate, or okay, I think 0 1, and that is 1 0. Okay, I need a NOR gate, right? Here my NOR gate input a y. So basically 0 0, my output is 1 0 1 0 1 0 0 1 1 0. So this is my NOR gate output. So I need a NOR gate. So just like that, here is the circuit, and here is the negative edge triggering circuit clock. So this is the my negative edge triggering circuit. And if we want like both at the same time positive edge triggering and negative edge triggering, then what we do? We just do the same circuit, like here we analysis. Okay. So, okay. Okay. So in here position, again in here we need a 1. In here position we need a 1. So how I can 1? So if we analyze the circuit like in cases, both cases, so here like both are 1, and here also both are 0. So how we get both 1 and both the 0? So this period also 1 trigger, and this period also 1 trigger. So it is nothing but we need a this is my clock, this is a NOT gate, some delay t, and this is my XOR gate, sorry, XNOR gate. Okay, this is my XNOR gate. So in both case, like we know 1 1 and 0 0, in both case XOR gate gives us 1 1. So this is my actually positive and negative edge triggering circuit. So D flip flop internal circuit to back to back latch, D flip flop internal circuit. Okay, clock bar, this is gives. Okay, so to back latch L1 and L2 controlled by complementary clocks. When clock equal to 0, L1 is transparent, L2 is opaque. Okay, and D passes through to N1. D passes through to N1. When clock is 1, L2 is transparent and L1 is opaque. N1 pass through Q. Thus, on the edge of the clock, when clock rise from 0 to 1, D passes through to Q. Okay, so what it tells, like here is clock and here is not gate. So when we gives the clock, suppose I gives the clock 0, so that time this circuit will not work. Okay, so what happen if we this circuit will 1? Suppose I give the 0 nanosecond delay, so whatever the D, suppose I give D equal to 1, so D goes to 1 here. Okay, and if D goes to 1 here, so suppose my clock is 0 this time period, and it changes here, and again changes here. Okay, so I want to see like this output, like what if my clock is 0, so this period clock is my 0, so that time this clock like D is 1, so that time D is 1 means like D gives me the output. So my output is like something I take here, the only one. So my output is 1, and same time here is 1, and after that this clock is on. If this clock is on, so my output also be on. Suppose if my changes here, any changes, so it changes and it's directly not changes actually, even it's hold the value, I think, for this period of time. Whatever the like your d input basically it's only this part. This part will goes to here. Only this part goes to output. Okay. So this the output, and again this period of time, and again this. And next cycle, if my output is like this, my output is like this. So this part, suppose my output is like this. So this initially this, and then this goes to this position, and again changes. So it's a like basically you can say master slave type of flip flop. But actually the clock, whatever the clock, that is actually the level triggering. So it's a flip flop, but also although it's a trigger in a this time. This time it's trigger in this period. It's will work. Basically here it is one when, then it is zero. When it is zero, then it is one. So that's the edge of clock when clock rise from 0 to 1 and D passes through Q. Now timing. Flip-flop samples D at clock edge. D must be stable when it is sampled. Similar to a photograph, D must be stable around the clock edge. If D is changing when it is sampled, and metastability can work. So flip-flops samples D at clock edge. Okay. So suppose it's a now comes to the static timing analysis basically. So here we have two flip-flop. So here flip-flop like D flip-flop, and here also D flip-flop. So here we gives the input D, and here some combinational circuit will be there, and again this combinational delay, like this combinational delay and some operations goes to the input of here. Okay, and here is the clock. Here is clock. Here is my clock. So this is my clock basically. This is and if the sequential circuit, then this output or here is some delay, and again this is the my goes to here, something like that. So basically flip flop, this is launching flip flop, and this is my capturing flip flop. D must be stable when it is sampled. Similar to a photograph, D must be stable around the clock edge. D must be stable around the clock edge. Similarly, to photograph, D must be similar to photograph, D must be stable around the clock edge. Similar to a photograph, D must be stable. Okay. At the clock edge, D must be stable. Okay. Now this concept I will tell you. Okay. Suppose my clock is this. And if my D input, suppose like my D input is here. And now I am using positive edge triggering. So in positive edge triggering, we see that my input here is D, and it is stable or not. Because for stable condition, like we don't switch from 0 to 1 or 1 to 0. This condition is not occur at this period of time when my clock is triggered. Okay, so this is actually the like conditions for metastability. Like my flip flop don't understood like what it takes either 0 or 1. So this is the main problem uh, of a flip flop. Like when clock is come, so if like the circuit, it is confused, like flip flop is confused, like what should we take, 0 or 1. This confusions is occur. So there are some setup time, some hold time, uh like they required. Like if suppose your clock is comes to here, so at least some previous time t setup time is required. So some t setup time you required setup, and some hold time also required, because in here setup time is not, like time is not issue. Setup time it holds, maybe setup time is 1 nanosecond, but is total 5 nanoseconds. So setup time is not issue, but the problem is the hold. My hold is also violating. So it goes to, simply it goes to the metastability condition. Similar to photograph, D must be clock if D is changing when the sampled metastability. So D is changing when it's sampled. So D change in this period, D is changing, then it goes to simply metastability. My like circuit will be like, suppose my input is this and clock is this, and if here it is changing, then it goes to like this, and it's after recover time, some recover time will be needed. So input time constants, setup time, t setup time before the clock age, that data must be stable. So I already told that before the clock age, my data should be stable here. Here in this period, data should be stable, and data must be stable. Okay, and whole time after the clock age, the data must be stable. So after the clock, so here is my clock and data must be stable. But here setup time is setup stable. Here whole time is like stable, not changing that much. So my here is the good position where hold and setup is not violating, but here it is violating, not changing. Should not be changed, but it's changed. And a aperture time, TA, time around clock age, that data must be stable. TA equal to T setup plus T hold. Okay, this is aperture time. Basically this is, so this is my clock, this is my clock, and here the T setup plus T hold, that is called aperture time. So in this period data must not be changed, otherwise it goes to metastability. Well, and output time constant, so propagation delay, TPCQ, time after clock is that the output. So time after clock is that the output. Q is guaranteed to be stable, stop changing, and contamination delay, TCCQ, time after clock is that Q might be unstable. So start changing. Okay, here is TPCQ and here is TCCQ. Contaminations. Actually, this is the clock to Q delay. So basically, here is my flip flop. This is my clock. This is my D, and Q is here. So this delay, clock to Q delay. So this is actually two type. One is propagation and one is contamination. Basically, the propagation comes for Ohm's time delay. So the circuit, in my circuit is like what is the maximum delay needed for my circuit to be stable. For my circuit, like TPCQ to be stable, TCQ like clock to Q should be stable. So that is the time, maximum time. What that is TPCQ, and the Base time delay, that is TCCQ. So clock to Q delay, but it is contamination delay, so circuit will be stable. If it's like transistor level, if we know the transistor level, so transistor level, what happened, like some kind of okay, I will tell. So suppose here is my one MOSFET, and here is my another MOSFET. It's a NMOS, here A, here B. So basically this is pull up network, and my sorry, pull down network, and my pull up network. Pull up network A, and here is B. Okay, and this is connected, and here we take the output basically. And okay, here my VDD, and here is my ground. Here is my ground. So what happened, here is my some capacitance, here is my some capacitance, here is 2 ratio, here is 2, and here is 2, and here is also 2, and some input capacitance, and here it is 2, that is 2C. Here is my some capacitor, that is 2, 2, 2, 2, 2, 4, 4 plus 2, this is 6C. So basically your propagation time delay is basically this capacitor also be charging, so it's not previously my B input is not 1, so that my this capacitor is not discharged like this way. So that's what, that we A and B at at the same time both are 1, at same time both are 1. So what happened, that this charging, whatever the delay, like there are some, here is my R, here is my R, so 6C R by 2, 6C R by 2, 6C R plus 2C into R by 2, so basically 7 RC. So this is my time required for propagation. But if it is already discharged, then I need only 6C R time. So only 6 year time I required. So this is my contamination delay, 6 year. If it is already discharged, so basically A equal to 0 and B equal to already 187, then A goes to 1. So if A goes to 1, then B already discharged. So this part will already discharge. So capacitor does not hold any charge. So whatever the charge is here, that will discharge like this way. So uh, this way. So my discharging time is 6 year. So basically that's the contamination delay and propagation delay difference. So here is clock. Clock is changing here. Also Q. Q is my output. So here the transition is happened. Something TCQ delay. T is clock to like contamination delay and Q. And here is also some like changes is happened due to capacitor. So that's the TPCQ. So this is the total propagation delay is TPCQ time after clock age that output Q is guaranteed to be stable to stop charging. So after that my output is purely stable. But in contamination delay, TCA time after clock age that Q might be unstable. So we don't know that this position will be happened or occur or not. So my TCQ contamination clock to Q delay, this is like little bit confusing. So if we like it sometimes it's maybe like unstable. That's the case we see. Dynamic discipline. The input to a synchronous sequential circuit must be stable during the aperture setup and hold time around the clock edge. So the input to a synchronous sequential circuit must be stable during the aperture setup and hold time around the clock's edge. Specifically, the input must be stable at least t setup before the clock edge, at least until t hold after the clock edge. So dynamic discipline, the input to a synchronous sequential circuit, the input of sequential synchronous sequential circuit must be stable during the aperture setup and hold. So aperture time we already see that my this is my setup and this is my hold. So basically this is my setup time and this is my hold time. So this is total my aperture time around the clock edge. So my clock edge should not be come here, or I can say that uh, sorry, my clock always comes to here, like uh, in this period the aperture time, this is called aperture time. So this aperture time period my data should be hold, it does not be changed like 0 to 1, 1 to 0 like that. Otherwise it goes to the metastability position. Specifically, the input must be stable at least t setup before the clock age. At least t setup before the clock. So here is my clock. Here is my clock. So before that, before here t setup is stable and after is hold. So here is my clock. Here is my clock. So before is this and after is this. This must be stable or like in a don't change like 0 to 1, 1 to 0. This condition will not be acceptable. So now comes to the dynamic discipline. So the delay between register has a minimum and maximum delay depend on the delays of the circuit elements. Okay, the delay between registers has a minimum and maximum delay depend on the delay of the circuit. Okay, so here is R1 and here is R2. Okay, here is Q1 and here is Q2, I think. Here is clock. Okay, that's the changes, and here that the changes in D2 as well. The delay between register has a minimum and maximum delay depend on the delays of the circuit. Suppose in this position we had this circuit. Okay, so this circuit also has some delay. So that's like minimum delay T minimum and T maximum. So basically, suppose my combinational circuit has this AND gate here, and this is one OR gate, and we take one not gate, and like this one and gate. So what happened? Like suppose this is one, this is one, and this is one, and this is also one. So what happened that this delay one clock unit delay. So I take, so here is one, here to here one, here to here one, here to here one, three. But in here to here one, and here to here one. So here 2 2 second required, na? So that's the problem. So the delay between registration minimum and maximum delay depend on the delays of the circuit elements. So but we never take the minimum delay. We always take the maximum delay because of some reason. Like suppose, what the problem with this? Okay, saved. Whatever I did, it's saved. Okay, so yes, I'll delete the PDF. So here I will be. So I give one example, that is here is one, and here also 1 plus 1, so it's required 2 nanosecond, but here is 3 nanosecond. So always we take the maximum delay, so that's what it uh, fulfill the circuit operation. Otherwise if we take one here and one this here, so total 2 nanosecond. So after 2 nanosecond, if we take 2 nanosecond minimum, then this circuit will change after sometimes, like after 1 nanosecond it will change. So at the position of 3 nanosecond, if we take start the circuit 0 to from 0, then at the 3 nanosecond the circuit might be changed. So that's we don't want to in our like input, so that we take the maximum delay, that is 3. The delay between register has a minimum and maximum delay depend on the delays of the circuit elements. Setup time constant. The setup time constant depends on the maximum delay from registers R1 through the combinational logic. The input to registers R2 must be stable at least T setup before the clock age. Okay, here is my clock. So here is my clock, and this is the TC. So TC should be TPCQ plus TPD plus T setup. Okay, so TC should be greater than TPCQ plus TPD, that is the propagation delay, plus T setup. So basically all are these should be maximum. Okay, that's why my TC should be like it's in a stable condition, or it's a like maximum time requirement, not maximum, like it's a minimum condition for TC. So setup time constants now. The setup time constant depends on the maximum delay from registers R1 through combinational logic. The input to registers R2 must be stable at least T setup before the clock age. So the setup time constant depends on maximum delay. So okay, maximum constants delay from registers R1 through the combinational logic. Okay. Okay, so I give you one example here. So suppose this is my one flip flop and this is my another flip flop. Okay, and here is my clock, and here is my combinational delay, the combinational delay. So this is flip flop 1, this is my D input, this is my, suppose this is my D1, this is my Q1, this is my D2, and this is my Q2. Okay, and here is clock, and suppose my combinational like clock to Q delay, I take some give some number, like my clock to Q delay this to this, clock to Q delay my T1, T1 this is max, and combo T2 that is also max, and okay, so basically okay, basically I want to write that my flip flop 1 and 2 both have some clock to Q delay, TCQ that is max, T setup some delay, T hold some delay will be there. So T hold also be like, I think it also be max. Okay, let's assume the circuit. So suppose here is T1, T2 and T3, and my combinational delay T combo is something like the T4. Okay. So now I I take a stable input, that is my D like D1 here. Okay, so that is my D1. So if this is D1 and this is my clock, suppose this is my clock, and now I check the clock like in this period, in this age and this age, because it's I take it's a positive age triggering flip flop, so that I check the previous here. Here I check the my setup time, and after that it's I check whole time and setup. So it's start from minus infinite, so that my D is always stable, like it's always a stable input. Otherwise, circuit will be like circuit analysis will be complex. So just a simple purpose, I take D1 is always one. And now what is my output? So if this is my this in this period, my clock is clock positive is triggered. So whatever the input at D1, that goes to the output at Q1. So here is my some delay, and this is my up to this, and again check. So the D1 is stable, so my output is 1. So this delay is basically nothing but TCQ, TCQ delay, like clock to Q delay. After clock to Q delay, my output is 1. And again, if my and after that, this is basically my D1. So now we need, sorry, this is my Q1. So we need D2. How we get D2? So there are some combo like combinational delay. So just take the combinational delay like this. So here is the TCQ and here is the T combinational delay like TPD. I assume TPD, and here's my output again. So this period TCQ plus TPD, and now again the clock of flip flop 2, that is also the same clock, because in clock there are no such delay, like no skew is present. So this positive edge we'll see here. Okay, so before that my out input is 0 because it is D2, so my input is 0, so it's not violate the setup time, but it's time for check to the whole time, that my whole time is violated or not. So if my whole time is T hold is less equal to uh, less equal to TCQ plus TPD, then it's good. Like my whole time is, if my whole time is TCQ plus TPD, then it's good. Otherwise, what happened? Like if my input is like my whole in the whole time, my clock to Q and TPD is much greater than T hold, that's okay. But if it is less than, then what's the problem? Then problem is like in whole time there some kind of 0 or 1 is like unconditional or non-desirable input will be there, so that time hold is violated. So my T hold is always less equal to less than, you can say, but sometimes equal to also be considerable. So TCQ to TPD. And what is the setup time? And next when the clock is coming, so this is the period for setup. So setup time should not be also violated. So for setup time I take the here is T2, and for whole time I take TCQ1 clock to Q delay. So that is basically a T1. So T1 and TPD some combinational delay, that is I take T4. So T4 and T2. So this is my total uh, clock time, that is T. So it should be greater than or equal to T1 plus T4 plus T2. So that is here also written the same thing. The TPCQ, that is the propagation delay of clock to Q, and TPD, that is the basically the combinational delay, and T setup. T setup basically the flip flop setup time. So this flip flop. So setup time constant. The setup time constant depends on the maximum delay from registers R1 through the combinational logic. The input to register R2 must be stable at least T setup before the clock age. So that's what I already told, that your circuit must be stable. So that time no uh, not change, like your input should not be changed. Otherwise it goes to metastability position. And hold time constant. So T hold I already told that less less than TCQ, TCCQ, or like TPCQ, and combinational delay. This is the combinational delay. So here we can see in this period my data should not be changed. So clock to Q delay and uh, and TPD combinational delay. So hold time constant. The hold time constant basically depends on the minimum delay from registers R1 through the combinational logic. The input to register R2 must be stable for at least T hold after the clock age. So that's what I already told, that the input to the register R2 must be stable for at least T hold after the clock age. Basically, whatever the clock age, here the clock age is. So T hold something, T hold will be required at this period of time. My data should not be changed. Here is T setup and T hold. So hold time constant. The hold time constant depends on the minimum delay from registers R1 through the combinational logic. The input registers R2 must be stable for at least T hold after the clock age. Okay. So that the combinational delay, I also the all the equations you can understood from here, that my T hold is like TCQ plus TPD, and my T clock at least T1 plus T4 plus T2. Okay, and whole time is like TCQ plus TPD. So it's basically my clock to Q delay is T1 plus, and my combinational delay is T4, that greater than to like T hold. So in this period, the T1 plus T4 time is always greater than the of my T hold time of my flip flop. So here is the timing analysis, timing characteristics. So one problem is here. Okay, let's check. Let's do this problem. So basically TPD setup time constant. Okay. So timing characteristic T clock to Q is 30 picosecond. Uh, sorry, this is contamination delay of clock to Q, and this is propagation delay. So we always take the propagation delay, and T setup is 60, and my t hold is 70. So if my t hold is 70 and the AND gate, there are some NAND and AND gate. So the par gate, okay. So we will take the propagation delay, the maximum delay. So here is 35 picosecond. Here is my 35 and here is my 35. So 35 into 33 into 35 is 105 picosecond delay is here. And my flip-flop delay, like clock to Q delay, so TPCQ propagation delay plus 50, so that's less than equal to my T hold, that is 70 picosecond. So the condition is achievable. So basically my this is my the hold time maximum, so we get 155 picosecond. So it's not violating. And my T setup time, now we need to check T setup time. So T setup is my, what is my T setup? 60. 60 plus 155. So that is basically 150 to 15 picosecond. So my clock to, so T clock is my 215 picosecond. At least. At least my T clock should be 215 picosecond. And TCD, what is the TCD, contamination delay and propagation delay? So here's the propagation delay is 105, like they are talking about this. So 105 picosecond. And the contamination delay, that is the best case delay, so that is the 75 picosecond. And what is the TCCQ plus TPD plus T hold? So basically that is the TC. Okay. So okay, I already told this is my, this is the like 155 and this is my hold is the T70. And the frequency is 1 by 215 picosecond. Basically picosecond is 10 to the power minus 12. So if I take the 1000, so it's almost like 250 if I assume. So 4 point something like that. And it should be like 4 point something like that, but it's in a into 10 to the power 9 hertz. So this is like megahertz. Mega or giga? Megahertz. Okay. Okay. So TCD my is 25 picosecond. What is par gate? But it's not proposed par gate. I don't understood why it is 25. But this is also my 2150. This is no. I understood it is no, because what? So let's see what is it is doing here. Add buffer to the short path. Okay, add buffer to the short path. So my no. Okay, this is 1570. This is not like 55 or something like that. TPD. So am I doing wrong here? No. TPD. Here, why it take 25? I don't understood. TPD. TCCQ. TCCQ is 30, but why it is TPD equal to 25 propagation delay? Not for one gate, because why should we take minimum? Oh, okay, understood, understood. The propagation delay, the TCD is contamination delay, clock, sorry, combinational delay, that is 25 picosecond, contamination delay, and TPD propagation delay. Okay, understood the concept now. and here is the my correct answer. But here what they did, so here the same question, but they add just buffer. If buffer is added, then I think contamination delay will be changed and propagation delay will be the same. I think like the maximum delay. Here the maximum delay is same, but the contamination delay will little bit change. And whole time constant, for whole time constant TCCQ plus TPD also we can take. Okay, so but setup time constants we don't change. Okay, so whole time can be like that 50 plus 30, so 80 picosecond. So you can take, but you can take that like setup time constant. You can't change. And target same questions. Now clock to skew. So the clock does not arrive at all register at the same time. So skew the difference between two clock edge. Examine the worst case of guarantee that the dynamic discipline is not violated for any registers may registers in the system. So here is the delay. So basically if I go through one an example, let's take clock to like clock skew delay. What is clock skew delay? Here is my flip flop one. Here is my flip flop two. This is my clock. Okay, and this is my one delay. Like suppose T skew SKW, and here is my clock. I don't know why it is not. This is my clock, and this goes to here, and here some combinational delay T combo. Here goes to here goes to here, and here also. So this is my D1, this is my Q1, this is my D2, and this is my Q2. Okay, and here is T skew. So what happened by adding T skew? So initially my clock is like suppose I my input, I take a input like this, the constant input I take, that is D1, and my clock is coming here. Okay, so in this period like positive edge clock, so just check that my D1 setup time or hold time is violated or not. So it's not violated, so it gives the output, but uh, in how much delay that will take, and after that this output will be shown at Q1. So here suppose my output is like this. Again it comes to here, so it will check again. So that time also we output one. Okay, so this delay, basically this delay I am talking about. So this delay is my TCQ of one, like clock to Q of flip flop one. So basically both are same I assume. So both are same to T clock to Q. Basically it's not TCCQ, it's TPCQ. Like propagation T, propagation to propagation clock to Q delay. Okay. So now this is the my Q2. Sorry, not Q2. This is my Q1, and this is my clock. Okay, clock of flip flop one. So now my combinational delay will come, and that's my like Q1 is. So here is my combinational delay sum, and here is my it's is the my D2. So what is d2? D2 is nothing but the delay of 2. 2 is what? One is tpcq and another is my tpd. Basically tpd is the propagation delay of this part, combinational delay of this part, that is I call tpd, and this is d2. And again, so now I uh, clock draw the clock again. Here is my clock want to come, but the some restrictions. So some restrictions will be there. My clock, sorry, my clock comes to here. Here clock wants to come, but the problem is that there are some delay because like suppose my flip flop is at the middle position, and like this is the buffer. Suppose this is the like some structure where like this flip flop is here and this flip flop is here, something like that, but your clock circuit is this, and this goes to this circuit, this clock. So this is the main problem, that yes, there are some delay will be occur in the between the two flip flop. So now if I make the clock, so my clock in identically should be here, but the problem is my clock some makes delay here, the delay, and again, so the clock delay like this. So this is my t skew. T skew is nothing but my t1 and minus t2 is different. Okay, so that is t skew. So t skew, suppose my clock is come at 0 second, but after 2 nanosecond and the clock clock 2 occur at flip flop 2. So this is basically 2 like that. Okay, if it is happened such a way so that it's now check this position. Okay, this position, so setup time is not violating, but chances to the violating whole time is, suppose my whole time is like something like that, this the whole time I required, so my input is changing. So d2 is my input, that is 0 to 1. So this is the main problem. It's possible to violated my hold condition, but if not, then it's will be good, because in this period, in the like suppose this, so this is your setup time, setup, right? So this is setup time. So suppose your setup time is here. So what is the actual clock? So from here to here, your actual clock time required. So basically, it's previously it was TCQ plus TPD plus T setup. But what happened now? Now it's changed. TCQ plus TPD plus T setup, and T skew. T skew is minus, basically. T skew is minus. So and it would be like minimum. It's not should not be maximum. Otherwise, like suppose if you take the maximum, so suppose this is 10, total 10 nanosecond, and this is your like something like that. T skew minimum is 1, and minimum is 1, and maximum is 2. Okay, suppose you take 2 like maximum, so what will be clock? 8. Your t clock is 8 greater than equal to 8 nanosecond. Okay, but suppose the sometimes like your propagation, your like t skew delay is 1. So that time, suppose your t skew like contamination delays happen in t skew circuit, like it comes to the early. early at 1 nanosecond. So then what happened? Your T clock required be at least 9, because 10 minus 1, so 9 required. But what we assume that we assume that our T clock is 8, so it's will be violated, and violated, some mismatch will be happen. So if my mismatch will be happened, then my T setup and T hold condition will be violated, and it again goes to metastability position. So that's we don't want to, like, unnecessary metastability condition we created. So I hope this T skew condition will be understandable. So setup time constants with clock skew. So in the worst case, the clock 2 is earlier than clock 1. So what I told already, that clock 2 is earlier, setup time constant. So TCQ, TPQ. So TCQ. If my TC, bolo. So basically, if my T clock should be like, if in the flip flop two, what happened that uh, my clock came to here first. So that time, if we assume to here, so suppose my two flip flop. So here flip flop one and here is flip flop two. Okay. So I assume that this flip flop is getting the clock fast. But what happened in this flip flop? There are some delay, some delay. So basically, Mhm. from here we get the uh, like we give the clock in the flip flop 2 and flip flop 1. But now I check the TPD from flip flop 1 to flip flop 2, because the flip flop 1 is my launching flip flop and flip flop 2 is my capturing flip flop, and there are some combinational delay between flip flop 1 and flip flop 2. So that what happened, when the like it's flip flop 2 getting the clock at early stage, but some delay maybe like 2 nanosecond or 3 nanosecond delay. After that, the flip flop 1, the occur clock occur at flip flop 1. So in previous, the what the equation I wrote, that is T clock. So basically T clock is nothing but that uh, some clock to Q delay plus a combinational delay, that is I take TPD, and plus some uh, flip flop delay, like, so clock to Q and TPD, and here some setup time delay. And in previous we take the negative T skew, so T skew, so negative. So in here the same equation also occur, like we can use, but the T skew here is negative. So if minus and this minus T skew, what happened? This is positive. So if my flip flop 2 get early clock compared to flip flop 1, then what's happened that if we uh, so if we see the changes of time, like from flip flop 1 to flip flop 2, like what the clock required, total required, so that time a T skew delay will be add. So even it will be not that much helpful, but also the whole time violation or this kind of violations will not even also occur. So this is the main good thing of this circuit. So setup time constants with clock skew. In the worst case, the clock 2 is earlier than clock 1. So what I already told. So that's why, like, my here minus and minus of T skew. So that makes the T skew positive. And what's the TPD? TPD is like that TPD. So my TPD will change. because here TPCQ plus TPD, sorry, TPD will not change, T hold will be changed, I think. T hold will be TPCQ or T skew. So this is the now total hold time. Here no hold time they will see, but okay. So basically TPD like that, and hold time clock to Q delay TCD like that. So in the worst case clock 2 clock 1, so they are just checking the TCD, and hold time constants with clock skew. So this is my hold time. So what is the hold time? Case 2, case 1, such that. So T clock to Q delay minus T skew plus TCCQ. Basically in worst case clock 2 is later the clock 1, but in clock 2 later than clock 1. So this is the clock 2 later than, but in case clock 2 later than clock 1, here I think earlier case. Okay, leave that conditions right now. So the violating conditions. So violating the dynamic discipline asynchronous, for example, user input might violating the dynamic discipline. So here is clock and hold. So T setup plus T hold, T aperture. So for example, inputs might violate the dynamic discipline. So here is button is like button is applied, like it's don't like no matter what it does not see, and button will occur, and the that time my clock also will be changed, and my D input. Okay, so here the D is my input. So condition case one that my D should not be changed. So my output will be like that, Q like that. So my D is not case one violating. Here also not violated. But here's what happened. So here's the metastability condition is come, and here is metastability. Any bistable device has two stable states and a metastable state between them. A flip-flop has two stable state, one at 0 and one metastability state. If a flip-flop lands in the metastable state, it could stay there for an undetermined amount of time. So it could stay there for an undetermined amount of time. So here is stable, but this is metastable and this is stable. Okay, undetermined of time. So it will be hold metastable state. If the flip flop lands in the metastable state, it could stay there for an undetermined amount of time. So flip flop internal, because the flip flop has feedback of Q somewhere between 1 and 0, the cross coupled gate eventually drive of the output to either rail 1 to 0, which close to no. Okay, this part is the like fast as we see in this PDF, that one page number 1, the same thing. So basically it's like some mismatch will happen, and this PDF, this page will come at the 38 number. So because the flip flop feedback, let's see what it's written here. If Q is somewhere in between 1 and 0, the cross coupled gates will eventually drive the output to either rail 1 or 0, depending on which one it is closer to, and the A's are the same. A signal is considered metastable if has not resolved 1 or 0. If flip-flop input changes at a random time, the uh, probability that output Q is a metastable after waiting some time t is. So P T reset greater than T naught by Tc to the minus T time. So T reset time to resolve to 1 or 0. So basically when metastability comes, so some resolve time will be needed to resolve the problem, like either 1 to 0, the circuit will decided, or flip flop will decided, and T naught and tau is the properties of the circuit basically. So metastability intuitively T naught by Tc describe the probability that the input changes at a bad time, i.e. during the aperture time. So basically P T reset greater than T. So T naught by Tc to the minus T by tau. Basically tau is time constant indicating how fast the flip flop moves away from metastability state. It is related to delay through the cross coupled gates in the flip flop. P of T reset greater than T, T naught by Tc to the minus T by tau. In short, if a flip flop sampled at a metastability stable input, if you wait long enough T, the output will have a resolve to 1 or 0 with high probability. In short, if flip flop samples a metastability input, if you wait long enough time, long enough T, the output will have a resolve to 1. Okay, it will say that if my clock period time like TCQ like TC, like clock, T clock equal to we already study, that is TCQ, clock to Q delay plus TPD, that is combinational delay plus T setup. T setup minus, I don't assume TCQ here, that we assume that flip flop 1 and flip flop 2 get the clock at the same time. So that uh, TCQ is 0 plus some recover time. Recover time for that if my uh, D, like flip flop one, as we already said that flip flop input of D is sometimes like the it's 0 to 1 or 1 to 0, that condition is occur. So that time we add a recover time. So which actually the recover time is basically the how fast the circuit will recover from metastability condition, either it 1 to 0. So uh, it got a certain uh, decision, that it makes a decision that the hold position either in 0 or 1, but not in both, like something like that is it goes to 1, but something like that this is not happened. So either 1 or 0, it's hold the value, and that's time, recover time. So uh, synchronizer is asynchronous input D are uh, inevitable user interface system with different clock interacting. The goal of synchronizer is to make probability of failure, the output Q still being metastable, low. A synchronizer can make the probability of failure 0. Okay, synchronizer internals. So here is the circuit. Okay, so for uh, like how to improve the from failure, like probability of failure. Okay, so what we did right now, we use a synchronizer circuit. Synchronizer circuit is nothing but a flip flop. So here is a flip flop and clock, and this is just like the flip flop 1 and flip flop 2 again, just like that, and clock something like that. So this circuit will used for improve improve our failure, like probability of failure. So probability of failure should be 0, so that we use synchronizer circuit. So synchronizer circuit, how it's work. So basically synchronizer circuit internals we will study. So basically previously what happened, like this circuit is not happened. So whatever the inputs we give, that will directly input of the flip flop 1. So there is no such synchronizer circuit will present. And so the previously the whatever the input comes, like whatever the input comes, that directly goes to here. So it does not wait for clock. So my circuit will be in this clock period. So the circuit directly goes to this. Okay, so this is the problem. And now what we did that we add a synchronizer 1 here, so that it stretch the circuit, it stretch the clock actually, basically. So my D input is like my clock is here. Okay, so D is my changing right now, like that. D is changing. D is changed. Okay. So what happened in this position? Like if we input D, so that time if my clock is not come here, then it will be not goes to metastability. But if suppose this goes to metastability, so this circuit will be resolve the problem. How it's problem? That is it, suppose somehow it's 0 or 1 already hold. This 0 is the, like some delay will be occur, like some delay from here to here, from here to here some delay will be occur. Okay, so that delay occurs. So I know that this circuit is goes to metastability. But whatever the output right now, that does not change because it change after TCQ delay. Okay, that time it's zero. Suppose it's sold and the clock is calm. So it's don't depend on the this circuit in metastability or not. If the clock is like that high and positive is triggering, so my already I have 0, but my other input be changed and it will be after t delay. After t delay it will be like something like that and come and it goes to 0. But that time my circuit is not like get the positive trigger. So whatever the output of this will not appear in the, like in this flip flop output. In this flip flop output it will not appear. So that what happened, uh, after sometimes like it's all or it's changed because this circuit changed, it's recovered. So after sometimes like it will goes to 1. So at that time my clock is again come and it see that, yeah, it's my this position is stable, so t setup is stable, so it goes to again 1. Here it is, we see 1. And if we for metastability, like we want to improve more, improvement more, so that time we add uh, two synchronizer circuit. And more than three it's not good because at that time also my T clock will increase. So if T clock increase, then my circuit will operate at lower frequency. Okay, so if my F equal to 1 by T, so if my T increase, then F decrease, so my circuit will be not that much fast. What the actual requirement, that circuit also be should be fast, like my from data from A to B, data from A to B goes fast, want to fast. Otherwise circuit slow, that it not meaning it like meaningless. So circuit should be fast. So more than three, it is unnecessary to add synchronizer circuit, and we see that how it works. And this is the synchronizer internal. A synchronizer can be built with two back-to-back flip-flops. Suppose the input D is uh, transitioning when it is sampled by flip-flop 1 F1. The amount of time the internal signal D2 can result to 1 or 0. That what I already told, that two flip-flop, like for synchronizer, two flip-flop will be extra, and maximum it will be 3, and more than that it will be not like that much effective because my T clock is increasing. So if T clock increasing, so frequency decreasing, and my circuit will be operate at um, a very less frequency and not that much speed. And synchronizer probability of failure. So for each sample, the probability of failure of the synchronizer is T naught by Tc e to the minus T setup by tau. So this is the failure for each sample probability of the circuit. Here is the failure T naught by Tc. So synchronizer mean time before failure. So this is actually the one problem comes in our exam also, that is MTBF. MTBF is the if a asynchronous input change 1 per second, once per second, the probability of failure per second of the synchronizer is simply P failure. In general, if the input change n time per second, the probability of failure per second of the synchronizer is, so P failure by second n T naught by Tc e to the minus Tc. So MTBF equal to 1 by P failure of the second. So MTBF formula will be one good formula. MTBF mean time before failure. So basically, mean time before failure is what I say. Uh, uh, After some times, like after at which time the circuit will be failure or what the chances of failure. So that is like the main chance. The what I say that this is the after at which time the circuit will uh, goes to the failure position. So this is MTBF. If the synchronous input changes once per second, the probability of failure per second of the synchronizer is simply P failure. In general, if input changes n times per second, the probability of failure per second of the synchronizer is P failure per second n T naught by Tc n T naught by Tc into e to the power minus Tc minus T setup by tau. So this is the conditions of P failure per second, and MTBF is what? 1 by P failure per second. So basically it is nothing but Tc by n T naught. Tc by n T naught e to the power T. Okay. Tc by n T naught e to the power minus Tc minus T setup by tau. And n is the time per second, and T naught is what? Probability T naught. T naught, I think the flip flop internal delay or something like that. TC is like confirmation delay or something like that. T setup is setup time. So example synchronizer. Suppose my TC is 1.5, so 2 nanosecond TC is okay, and T naught is 150 picosecond, and n equal to 10 events per second. Okay, and tau is 200 picosecond, and T setup equal to 100. And so my MTBF is T naught by n T naught NTC. So 150 by 20, 10 events, e to the power minus, sorry, e to the power t, t is what? E to the power t minus 100 into 10 to the minus 12. I think this is the my conditions. Let's see. MTBF is like P failure per second. Okay, failure per second. 150 picosecond by 2 nanosecond into e to the power minus 1.9 nanosecond by 200 picosecond. Okay, basically 1.9 nanosecond. Where I get nanosecond, 2 nanosecond is here. Okay, TC minus T setup, I think. E to the power minus, okay, TC minus T setup. So here is TC, so minus T setup, so that is 1.9 nanosecond, and by TC minus T setup by tau. Tau is 200 picosecond. So this is 200 picosecond, and 150 picosecond by 2, 150 picosecond by 2. So that is 5.6, 2 or 20, 2. mm, 100. So by 2 nanosecond. Okay, it's multiplied, na? So that p failure per second, 10 events. So p failure n events per second is 5.6 into 10 to the minus 5. So MTBF is 1 by p failure. So 5.6 into so 5 hours mean time before failure. So this is the MTBF. Okay, so I discussed this 45 pages of PDF where I discuss little bit of SR latch and how to make D latch by using SR latch, and thereafter like more problems I solved from STA. I discuss STA static timing analysis, and also giving some questions with solving problem of skew. So skew like the flip flop 1 and flip flop 2 delay, like clocks are not coming at the same time. Sometimes like clock 2 get the time clock flip flop 2 get the clock time before then flip flop 1, and sometimes the flip flop 1 is the like get the clock compare early, get the clock early compared to flip flop 2. So that's kind of problem I solved. So hope this video will be helpful for the guy who are preparing for placements for digital design role, or some others role like digital verification also, maybe it will help. Okay, so that's all from my side. And if you don't know me, basically my name is Pallab Pal. Currently I am pursuing MTech from IIT BHU. Okay, that's all guys.